Hey, it's Doc Williams, and in this video, we're going to write equilibrium constant expressions and then use them to calculate problems. Now, writing an equilibrium constant expression, we will follow this chemical equation, which is KEQ. K stands for the equilibrium constant, and we're going to write the products, or I should say the concentration of the products over the concentration of the reactants. And that's what the brackets mean, is concentration. So when we see concentration, we're talking about the units of moles over liters, which is molar. To illustrate how we're going to write these chemical equations into that equation, I'm going to write a generic chemical equation, which we will use to plug into all the parts. Now, A plus B going to C plus D is a reversible reaction. And if you notice, all of the reactions on this page are reversible reactions. And then our coefficients are just going to be the lowercase of each letter. So now let's plug this into our equation. We're going to have the concentration of our products, which are D and C, over the concentration of our reactants, which are A and B. Now, so far we have the actual compounds or elements, and we need to add our coefficients. So our coefficients are going to be what we raise each one to, meaning we're going to write these as exponents at the top. So let's follow this format for each one of our examples at the bottom. So for this first one, the chemical equilibrium constant will be the concentration of our products, which is CS2 times H2, and we're going to raise each of those by its coefficient. Whenever we do not see a number, it's understood to be 1. But when we see a number, we're going to put that number as our exponent and raise only the element that that coefficient pertains to that power. So in this case, only the H2 is raised to the 4. Now let's write our products. We have CH4, so the concentration of CH4, and notice that the subscript goes inside of the brackets because that is part of your chemical formula. And we have H2S. CH4 is raised to 1. You do not have to write anything there. It's understood to be 1. And then H2S is raised to the second power. This is our equilibrium constant expression for number 1. Let's look at number 2. Following what we did above, we will write our equilibrium constant as our products, over our reactants. However, if you notice with the first one, we had all gases, and this one we have aqueous in our products and a solid in our reactants. Now, for equilibrium, we only are concerned about our aqueous solutions and our gases. Solids we do not include, and liquids we do not include. This is because solids and liquids at equilibrium, their concentrations really don't change. So we're really calculating the concentrations for our aqueous and our gases. So in this case, we will not write the solid, but we will definitely write both of our aqueous solutions. So instead of having our products and reactants, we would just be writing our products. Oh, this 2 should not be here. We're crossing out this 2 because we have 2 lithium here and 2 lithium here, which means we have a balance equation. So in order to write our products, we have lithium ion raised to the second power, and we have CO3 -2. If you notice, the charges are going inside. The only thing that goes outside for the power is the coefficient, in this case 1. So when there's a 1, we do not have to write it. And this is the equilibrium constant expression for this problem. For number 3, we see that we have a solid breaking down or decomposing into a solid and a gas. We do not include our solids based on what we saw up here, but we do include the gas. So in this case, our equilibrium constant expression will have only one, which is the oxygen, the O2, raised to the third power. Pause the video and write the equilibrium constant expression for number 4. Number 4, we have H2, which is a gas, and Br2, which is a gas, breaking, or I should say, combining to form HBr2, which is a gas. So all of these will be included in our equilibrium constant, writing our products at the top, and it's going to be raised to the second power, and then our reactants at the bottom. And since neither of these reactants have a coefficient higher than 1, we do not need to write anything there. And this is our coefficient, or I should say our equilibrium constant. Now we're going to use what we learned about writing equilibrium constant expressions to solve problems. This first one says, what is the equilibrium constant for the following reaction at 25 degrees Celsius if the concentration of NO is 0.106 molar, the concentration of O2 is 0.122 molar, and the concentration of NO2 is 0.129 molar. And you have a balanced chemical equation. Sometimes you're not given an equation, and in those cases, you will need to write the equation and balance it before moving forward because you need those coefficients to be able to plug into your equilibrium constant expression. So in this case, our product is NO2 raised to the second power because we have a coefficient of 2. In our two reactants, we have NO raised to the second power times O2 just raised to the first. At this point, since we have our equation, it's just a plug and chug. We're going to write the concentration of NO2, which is 0.129 molar squared. Don't forget your squared. Then we're going to write our concentration of NO, which is 0.106 molar squared, and the concentration of our oxygen. When you're putting these into your calculator, I strongly recommend that you use parentheses because if not, it's going to do the PEMDAS out of order. So make sure you're using parentheses where you need to. The answer for this equilibrium constant is 12.1 to 3 significant figures, and we do not have any units since all of the units cancel out. In this problem, we're given the units as moles per liter. If you remember from the first one, moles per liter is molar, so we're fine here. And it says calculate the equilibrium constant for the following reaction if the equilibrium concentrations for PCl5 is 0.0096 moles per liter, PCl3 is 0.0247 moles per liter, and Cl2 is 0.247 moles per liter. We're going to start by writing our equilibrium constant, which are our concentrations of our products. And since we do not see any coefficients, it's understood to be 1. We do not need to write any exponents. And this is going to be over PCl5. Now we just plug in our concentrations. So for PCl3, we have 0.0247 moles per liter. For Cl2, 0.247 moles per liter. Let me correct this. And then for PCl5, 0.0096 moles per liter. And this gives an equilibrium constant of 0.64, keeping in mind that our least number of sig figs is 2, so our answer is reported to only 2 sig figs. This question is going to ask us something a little bit different. So at a given temperature, the equilibrium constant for the following reaction is 1.40 times 10 to the negative 2. If the concentration of both H2 and I2 at equilibrium are 2.00 times 10 to the negative 4 molar, find the concentration of HI. We're given the equilibrium constant and asked to find one of the concentrations. We will still follow the same process, but then just solve for the missing concentration. So beginning with our equilibrium expression, we have our concentration of H2 times our concentration of I2, because everything here, forgot that, so everything here are gases, so we're going to include everything in the equation, all over the concentration of HI raised to the second. So going ahead and plugging in my numbers, I have 1.40 times 10 to the negative 2 for the equilibrium expression, divided by 2.00 times 10 to the negative 4 molar times 2.00 times 10 to the negative 4 molar. And I know this because it tells me that both of these, H2 and I2, are 2.00 times 4 to the negative molar. And I'm going to keep this as HI raised to the second power because this is what I'm solving for. Now I want to get HI squared by itself. And to do that, I am going to first multiply both sides by this concentration, HI squared. We'll cancel out here, and then that will give us times 1.40 times 10 to the negative second. And instead of just writing this out each and every time, I'm going to go ahead and square my 2.00 times 10 to the negative 4, and that gives 4.00 times 10 to the negative 8 molar. The next step is to divide each side by 1.40 times 10 to the negative 2. On this side, it would cancel out, leaving just my HI squared equals 2.85714 times 10 to the negative 6. I wrote more numbers here to give us a better estimation when we're rounding, and that would be molar. Now, in order to get the concentration of HI by itself, we're going to need to take the square root of both sides. That gets rid of the square here, which gives a final concentration for HI to be 0.00169 molar. Be sure to hit like if this video was helpful and subscribe to know when more equilibrium videos post. And as always, thank you for watching.